Right now, there are approximately 25,000 asteroids large enough to destroy a city orbiting near Earth, and we have found fewer than half of them. Every single day, our planet crosses paths with debris left over from the violent birth of the solar system. Most of it burns up harmlessly, but roughly once every century, something big enough to level a metropolis slips through undetected. The terrifying truth is not that scientists have identified one giant rock aimed directly at us. It is that the real danger hides in what we have not found yet, in objects too dark, too fast, or too close to the sun for our telescopes to catch in time. The question is not whether Earth will be hit again. The question is whether we will see it coming. If you want to understand the real science behind the most dangerous objects in our solar system, go ahead and hit that like button and subscribe. It helps more than you know, and I genuinely appreciate every single one of you who supports this channel. Now, let's begin. Close your eyes for a moment and imagine the worst day in the history of this planet. 66 million years ago, a rock roughly 10 to 15 kilometers wide entered the atmosphere above what is now the Yucatan Peninsula in Mexico at a speed of approximately 20 kilometers per second. It did not slow down appreciably. It did not skip off the atmosphere. It punched through the air so fast that the atmosphere in front of it compressed into a superheated sheath of plasma, hotter than the surface of the sun. The impact released energy equivalent to roughly 10 billion Hiroshima bombs. A wall of molten rock sprayed into the upper atmosphere and rained fire across an entire hemisphere. Tsunamis hundreds of meters tall raked every coastline facing the Gulf of Mexico. The shockwaves circled the globe multiple times. Soot and sulfur choked the skies for years, collapsing photosynthesis and freezing the planet. 70% of all species went extinct, including every non-avian dinosaur that had dominated life on Earth for over 160 million years. That is the image most people carry when they hear the phrase dangerous asteroid. A civilization-ending hammer from space, a single catastrophic event that rewrites the biological history of an entire world. It is dramatic, cinematic, and real. It happened. The crater is still there, buried beneath the seafloor near Chicxulub, roughly 180 kilometers across. You can measure it with satellites. But here is what that image gets wrong. It makes you think the danger is binary. Either a giant rock is coming to kill everything, or we are fine. Either the apocalypse is scheduled, or there is nothing to worry about. That framing is not just misleading. It is the single biggest reason most people fundamentally misunderstand the actual asteroid threat facing our planet right now. The terrifying truth is not that one known asteroid is secretly guaranteed to hit us. It is that asteroid danger is a constant, real, planetary defense problem shaped by probability, detection limits, and the physics of impact consequences. And the moment you understand how that system actually works, you realize the situation is far more unsettling than any Hollywood disaster movie has ever shown you. Let us start with the basics. The solar system is not a tidy place. It looks clean in textbook diagrams where planets follow neat elliptical orbits with generous spacing between them. In reality, our cosmic neighborhood is littered with debris. Billions of rocks left over from the formation of the solar system 4.5 billion years ago still orbit the sun in every conceivable configuration. Most of this material lives in the main asteroid belt between Mars and Jupiter, a broad donut-shaped region containing millions of objects ranging from dust grains to dwarf planets. But the belt is not a wall. It is not a fence. Gravitational interactions with Jupiter and the other planets have been kicking objects out of stable belt orbits for billions of years, scattering them across the inner solar system like billiard balls disturbed by a careless elbow. Some of those scattered objects end up on orbits that cross the path Earth takes around the Sun. When they do, they earn a specific designation. They become near-Earth objects. A near-Earth object, or NEO, is any asteroid or comet whose orbit brings it within 1.3 astronomical units of the Sun. 1 astronomical unit is the average distance between Earth and the Sun. roughly 93 million miles or 150 million kilometers. Anything that comes within about 30 million miles of our orbital path qualifies. As of late 2024, astronomers had discovered over 37,000 of these near-Earth objects. The vast majority, more than 99%, are asteroids rather than comets. They range from tiny rocks a few meters across to massive bodies several kilometers wide. And new ones are being found at a rate of roughly 3,000 per year. Now, not all of these objects are dangerous. Most near-Earth asteroids are small, and even those on orbits that theoretically intersect Earth's path may never come particularly close in practice. Orbits are three-dimensional. Two objects can cross the same orbital plane without ever occupying the same point in space at the same time. The critical distinction comes when you apply two specific filters. First, does the asteroid come close enough to Earth's orbit to pose a realistic collision risk? NASA defines this as a minimum orbit intersection distance of 0.05 astronomical units or less, which works out to about 4.6 million miles. Second, is the asteroid large enough to cause significant damage if it did hit? The threshold here is an absolute magnitude of 22 or brighter, which corresponds to a diameter of roughly 140 meters or more. An asteroid that meets both criteria earns the classification Potentially Hazardous Asteroid, or PHA. As of early 2025, approximately 2,465 objects carry that label. That number is important, but it requires careful interpretation. Potentially hazardous does not mean it is going to hit us. It does not mean scientists are worried about a specific collision date. It means the object's orbit and size place it in a category that warrants sustained monitoring. The label is about orbital geometry and physical capability, not about imminent threat. An asteroid can be classified as potentially hazardous and remain on that list permanently even after a collision has been ruled out for the foreseeable future, simply because its orbit continues to bring it close to ours. This distinction matters because it is the first place where public understanding diverges sharply from scientific reality. When a headline announces that a potentially hazardous asteroid is approaching Earth, most readers interpret that as danger. Scientists interpret it as a classification criterion being met. The gap between those two interpretations is where nearly all asteroid panic originates. And closing that gap requires understanding something deeper about how these objects are organized. Near-Earth asteroids are divided into 4 orbital families based on the shape and position of their orbits relative to Earth's. And more asteroids approach Earth's orbit from the outside but do not cross it. They come close but never actually intersect our path. Apollo asteroids have orbits that do cross Earth's orbit and have semi-major axes larger than Earth's, meaning they spend most of their time farther from the Sun than we are, but periodically sweep inward past us. Aten asteroids also cross our orbit but have smaller semi-major axes, meaning they spend most of their time closer to the Sun than Earth. And Atira asteroids have orbits entirely inside Earth's orbit, never venturing beyond our distance from the Sun. Each family presents different detection challenges and different threat profiles. Apollos are the most numerous among known near-Earth asteroids, partly because they are easier to spot from Earth when they are on the outbound portion of their orbit, moving away from the Sun into the dark sky where telescopes work best. Their orbits carry them outward past Earth and into the region between Earth and Mars, where they spend much of their time visible against the dark background of deep space. Survey telescopes love Apollos. They are the low-hanging fruit of asteroid detection. Atens are trickier. Because their orbits are mostly interior to Earth's orbit, they spend a large fraction of their time between Earth and the Sun. From our perspective on the ground, that means they are frequently lost in the solar glare, the bright wash of scattered sunlight that dominates the daytime sky and the twilight horizon. Ground-based telescopes can only observe effectively in the darkest parts of the sky, pointed away from the Sun. Atens that happen to be on the far side of their orbit from us, temporarily beyond Earth's distance from the Sun, are observable. But when they swing back inside our orbit and approach from the sunward direction, they effectively vanish from our detection network. Asteroids are the most elusive of all. Their entire orbits lie inside Earth's orbit. They never venture beyond our distance from the Sun. From the ground, they are perpetually buried in the brightest part of the sky, visible only in brief windows during twilight when they happen to be at maximum angular separation from the Sun. We have found fewer than 30 Atira asteroids as of 2025, a number that almost certainly represents a tiny fraction of the true population. Some models suggest hundreds or even thousands of Atira-class objects exist that we have simply never been able to see. This is not a minor technical footnote. It is one of the most critical gaps in our planetary defense. The geometry of sunlight creates a blind spot in our detection network, and that blind spot is not small. An asteroid approaching Earth from the sunward direction can remain invisible to every ground-based survey telescope on the planet until it is extremely close. The Chelyabinsk meteor that exploded over Russia in 2013 came from a sunward direction. Nobody saw it coming. Not a single telescope, not a single automated survey, not a single astronomer anywhere on Earth detected it before it detonated in the atmosphere with enough force to damage thousands of buildings and send more than 1,000 people to the hospital. It was only 18 meters across. No telescope on Earth saw it until the sky was already burning, and it arrived without any warning whatsoever. That event alone should have permanently changed how the public thinks about asteroid risk. But because no one died and because the footage looked more spectacular than lethal, it faded from public consciousness within weeks. The lesson it carried, however, remains urgent. The solar system contains objects capable of causing enormous destruction at scales well below the civilization-ending threshold, and many of them are invisible to our current detection infrastructure. Here is where the numbers become genuinely uncomfortable. In 2005, the United States Congress passed the George E. Brown Jr. Near-Earth Object Survey Act, which directed NASA to detect, track, catalogue, and characterize at least 90% of all near-Earth objects, 140 meters in diameter or larger, by the year 2020. 140 meters is the rough threshold above which an asteroid impact could cause catastrophic regional devastation. An object that size striking land could destroy an area the size of a major metropolitan region. Striking ocean, it could generate tsunamis capable of devastating coastlines hundreds of kilometers from the impact point. Congress set the deadline because scientists made clear that these objects represented a real and quantifiable threat that justified systematic action. The deadline passed. NASA did not meet it. Not because of negligence or incompetence, but because Congress never appropriated dedicated funding for the task. The mandate was, in effect, an unfunded demand. Lawmakers told NASA to find 90% of the most dangerous near-Earth objects, but did not provide the budget to build the tools required to do so. The surveys that existed, primarily the Catalina Sky Survey in Arizona, the Pan-STARRS telescopes in Hawaii, and later the Atlas system spread across multiple sites globally, were doing extraordinary work with limited resources. They found thousands of near-Earth objects every year. They pushed the discovery rate from a trickle to a flood. But finding 90% of a population estimated at roughly 25,000 objects requires capabilities that ground-based telescopes alone cannot deliver. The atmosphere blurs images. Weather shuts down observations for days at a time. And that persistent sunward blind spot means an entire population of asteroids remains hidden regardless of how powerful your ground-based telescope is. As of early 2025, approximately 44% of near-Earth objects above the 140-meter threshold had been catalogued. 44%. After 2 decades of searching with the best survey telescopes humanity has ever built, we are not even halfway to the goal Congress set. That means more than half remain undiscovered. Somewhere out there, roughly 14,000 asteroids large enough to obliterate a city or devastate an entire region are orbiting the Sun on paths that cross near-Earth's orbit, and we do not know where they are, how big they are, what they are made of, or when they might come close. And the problem extends well below the 140-meter threshold. Objects between 20 and 140 meters are far more numerous and far harder to detect. Estimates suggest there may be millions of near-Earth objects in the 20 to 50 meter range alone. Most of these would not end civilization, but they could destroy a city, flatten a region of countryside, or generate devastating tsunamis if they struck near a populated coastline. The Chelyabinsk impactor was only 18 meters, and it still managed to hospitalize hundreds, damage thousands of structures, and cause tens of millions of dollars in economic loss. Scale that up to a 50-meter object, and you are looking at an explosion in the multi-megaton range. Enough to level a city the size of London or Tokyo, if the geometry of entry happened to align with a populated area. Let that settle for a moment. This is not speculation. This is the official assessment from NASA's own Planetary Defense Coordination Office. The objects exist. The gap in our catalogue is measured and acknowledged. The only question is how quickly we can close it. The answer to that question is finally taking shape. NASA's NEO-Surveyor mission, the first space telescope ever designed specifically for planetary defense, is scheduled to launch no earlier than September 2027. Operating from the Sun-Earth Lone Lagrange point, roughly 1.5 million kilometers from our planet, NEO-Surveyor will scan the solar system in infrared wavelengths, detecting the thermal signatures of asteroids rather than relying on reflected sunlight. This is transformative because it solves two problems at once. Dark asteroids that reflect very little visible light, and asteroids lurking in the sun's glare where optical telescopes cannot see, will both become detectable. Over a 5-year baseline survey, NEO-Surveyor is designed to find at least 2/3 of the remaining undiscovered near-Earth objects above 140 meters, with an extended mission goal of reaching the 90% threshold Congress mandated over 2 decades ago. But until that telescope is operational, we are flying partially blind. Every month, the Minor Planet Center, which serves as the global clearinghouse for asteroid observations, processes thousands of new positional reports from observatories worldwide. Every week, newly discovered objects briefly appear on impact risk tables maintained by NASA's Sentry system and ESA's Near-Earth Object Coordination Center, before additional observations refine their orbits and the threat evaporates. This is normal. This is exactly how the system is supposed to work. Initial orbits calculated from just a few nights of observation carry enormous uncertainty. The asteroid could be in any number of slightly different trajectories, and some of those trajectories might intersect Earth at some future date. More data reduces uncertainty. The range of possible orbits narrows, and almost every object that appears on a risk list disappears within days or weeks, as astronomers pin down its true trajectory with enough precision to rule out a collision. NASA's Sentry 2 system, which replaced the original Sentry in 2021, performs this analysis automatically and continuously. It scans every known near-Earth asteroid orbit, projects it forward 100 years, and calculates the probability of any future Earth impact. The system is sophisticated enough to account for non-gravitational forces, including a strange thermal phenomenon called the Yarkovsky effect that can slowly nudge an asteroid's orbit over decades by enough to make the difference between a miss and a hit. Sentry 2 runs these calculations for every object in the catalogue and publishes the results in real time on a public risk table that anyone can access. As of early 2026, roughly 1,900 near-Earth asteroids sit on that risk table. That sounds alarming until you understand what the table actually represents. The vast majority of these objects are small, most well below the 140-meter threshold. Their impact probabilities are vanishingly low, often less than 1 in a million. And nearly all of them are what scientists call virtual impactors, objects where the orbital uncertainty technically permits an Earth intersection, but where the actual probability is negligible. Only about 21 objects on the entire risk table are large enough to qualify as potentially hazardous. None currently rate above 0 on the Torino scale, which means none represent a level of risk that warrants public concern under the internationally agreed assessment framework. Almost every object on the list will eventually be removed, as additional observations eliminate the remaining orbital uncertainty. This is not a failure of the system. It is the system working exactly as intended. You cast a wide net, catch everything that could conceivably pose a risk, then systematically eliminate false alarms through better data. The list shrinks. The real threats, if any exist, remain. Almost every object. The case of asteroid 2024 YR4 demonstrated what happens when the system encounters an object that refuses to cooperate quickly. Discovered in late December 2024 by the Atlas Survey Telescope in Chile, this roughly 50-meter asteroid was initially assessed with a greater than 1% chance of impacting Earth on December 22, 2032. That might not sound like much, but in the context of asteroid risk, it was extraordinary. A 1% impact probability is a screaming alarm. For comparison, the background probability of any random asteroid hitting Earth on any given date is measured in billionths of a percent. 1% is millions of times above the noise floor. Within weeks, the probability climbed higher as initial observations were processed. At its peak, the impact probability reached approximately 2.3%, and the asteroid was assigned a rating of 3 on the Torino scale, the highest active rating on any risk table at the time, and only the third object in history to exceed a rating of 1. Headlines erupted. Social media panicked. Misinformation spread faster than any official update could correct. Then the system did what it is designed to do. Astronomers around the world coordinated observations through the International Asteroid Warning Network. Ground-based telescopes tracked the object as long as it remained visible, and as more data refined the orbital solution, the probability began falling. By late February 2025, the impact probability had dropped below 1 in 1,000, and the Torino scale rating returned to 0. By March 2025, the risk to Earth for the 2032 encounter was calculated at roughly 1 in 120,000. The crisis, such as it was, had passed, but the story did not end there. As the asteroid receded from Earth and became too faint for ground-based telescopes to observe, a new question emerged. Could it hit the Moon instead? The orbital uncertainty, while dramatically reduced for an Earth impact, still permitted a small possibility of a lunar strike on the same date. To resolve this, NASA made the extraordinary decision to use the James Webb Space Telescope, the most powerful space observatory ever built, to observe a tiny, faint asteroid at the extreme edge of its detection capability. In February 2026, Webb captured observations that refined the orbit sufficiently to rule out both an Earth and a lunar impact. The asteroid is now confirmed to pose no significant threat for the next century. This episode is not a story about a near miss. The asteroid was almost certainly never going to hit Earth. What it is, however, is a perfect illustration of how the system works, how the public reacts, and why the gap between those two things is itself a form of danger. The real risk is not that scientists will fail to detect a threatening object. The real risk is that by the time an object is detected, there may not be enough time to do anything about it. And that brings us to the most important concept in planetary defense, one that most people have never considered. The danger of an asteroid is not determined solely by its size. It is not determined solely by its speed, or its composition, or even its orbit. The single most important variable in whether an asteroid poses a genuine threat to human civilization is something far simpler and far more terrifying. It is time. How much warning do we get? How many years, months, weeks, or days elapse between the moment we discover an object and the moment it reaches Earth? Because every mitigation strategy humanity has ever conceived, every deflection technique, every evacuation plan, every emergency protocol depends entirely on that window. A 1-kilometer asteroid discovered 30 years before impact is a solvable problem. A 50-meter asteroid discovered 3 weeks before impact is a catastrophe we can do nothing about except brace for. The public conversation about asteroid danger, almost always focuses on the wrong variable. People ask how big is the asteroid, when the question that actually determines whether we live or die is how early did we find it. Size determines consequence. Warning time determines whether we have any options at all. And right now, for a significant fraction of the near-Earth asteroid population, the answer to that question is, we would not find it early enough. This is the real threat landscape. Not a single doomsday rock with a name and a date. Not a secret government cover-up. Not a conspiracy of silence. The threat is structural. It is a permanent feature of living in a solar system filled with debris, orbiting a star surrounded by gravitational chaos, on a planet that has been struck thousands of times before and will be struck thousands of times again. The threat is that our detection system, while remarkable and improving every year, has gaps. Real gaps. Gaps measured in thousands of undiscovered objects. Gaps created by the geometry of sunlight. Gaps defined by the physics of faint, dark, fast-moving rocks against the black background of space. No known asteroid is on a confirmed collision course with Earth. That statement is true, and it is genuinely reassuring. NASA and ESA continuously monitor the skies, and their automated systems scan every known near-Earth object for potential impacts over the next 100 years. As of right now, no object on any risk table rates above 0 on the Torino scale. There is currently no known significant threat of impact for the next century or more. That is the official position of every major space agency on the planet, and it is grounded in real data and rigorous analysis. But that phrase, no known threat, carries a qualifier that most people gloss over. Known. We can only assess the risk from objects we have found, and we have not found them all. Not even close. The Sentry system is extraordinarily good at what it does, but it can only evaluate orbits that have been measured. It cannot assess the danger from an asteroid that has never appeared in any telescope. It cannot calculate an impact probability for an object that does not yet exist in any database. The system protects us from known threats with impressive reliability. It offers no protection whatsoever against the unknown, and the unknown is not a small category. When more than half of all near-Earth asteroids above 140 meters remain uncatalogued, and when the population of smaller but still destructive objects in the 20 to 100 meter range is almost entirely uncharted, the phrase "no known threat" begins to sound less like an all-clear signal and more like an honest admission of incomplete information. It is the difference between a doctor saying your test results are clean and a doctor saying we have not run all the tests yet. The universe does not wait for our surveys to finish. Asteroids do not pause their orbits while we build better telescopes. Every single day, Earth sweeps through a region of space populated by objects we have catalogued and objects we have not. The ones we know about, we track with extraordinary precision. The ones we do not know about move through the same space, follow the same physics, and carry the same destructive potential, entirely invisible to our instruments. The gap between what we know and what exists is the space where real danger lives. And everything that follows in this story will show you exactly how wide that gap remains, what we are doing to close it, and why the race between discovery and impact is the most important scientific effort most people have never heard of. What comes next will change how you think about danger itself, because the asteroids that should worry you most are not the ones with famous names and dramatic headlines. They are the ones nobody has seen yet. And understanding why requires looking at something most people never consider. What actually happens when a rock from space meets the thin blue line of our atmosphere? That physics is where the real terror begins. On the morning of February 15th, 2013, residents of Chelyabinsk, Russia, were commuting to work under a clear winter sky. At 9:20 local time, the sky split open. A blinding fireball brighter than the sun streaked across the horizon from east to northeast, casting sharp double shadows on the snow-covered streets below. For roughly 30 seconds, people stopped, stared, and reached for their phones. Then the shockwave arrived. The blast wave from the airburst shattered windows across 6 cities. Glass exploded inward on school children sitting at their desks. Factory walls buckled. A zinc factory's roof partially collapsed under the pressure differential. Over 7,000 buildings sustained damage. More than 1,400 people were injured, the vast majority cut by flying glass. The flash was so intense that some people suffered temporary retinal burns and ultraviolet skin damage from the light alone, even at distances of dozens of kilometers from the trajectory. We discussed this event briefly as an example of a detection failure, but the physics of what actually happened above Chelyabinsk reveals something far more important than a missed object. It reveals the anatomy of asteroid danger, and it proves that the variables determining destruction are far more complex than most people realize. The Chelyabinsk object was approximately 18 to 20 meters across and weighed roughly 12,000 to 13,000 metric tons. It entered the atmosphere at a shallow angle of about 18 degrees from the horizontal, traveling at approximately 19 kilometers per second. That is nearly 56 times the speed of sound. At that velocity, the asteroid was crossing roughly 19,000 meters of atmosphere every second. The air in front of it could not move out of the way fast enough. It compressed into a superheated cushion of plasma reaching temperatures of several tens of thousands of degrees. The surface of the asteroid began ablating violently, shedding material in a trail of incandescent vapor. But the critical event was not the fireball. It was the fragmentation. At an altitude of roughly 30 to 40 kilometers, aerodynamic forces overwhelmed the structural integrity of the rock. The asteroid was a stony object, an ordinary chondrite made primarily of silicate minerals with some embedded metal grains. Stony asteroids are not monolithic boulders. Many are fractured, riddled with internal cracks from billions of years of collisions in space. When atmospheric pressure built to the point where it exceeded the tensile strength of the rock, the asteroid shattered. Not into 2 or 3 pieces, but catastrophically, into thousands of fragments that spread across the sky like a shotgun blast of superheated stone. This fragmentation event is what created the airburst. When a solid object breaks apart at hypersonic speed, its cross-sectional area exposed to atmospheric drag increases explosively. The fragments decelerate far more rapidly than the intact body would have. The kinetic energy that was previously distributed across a single object is now being dumped into the atmosphere all at once. The result is a massive release of energy centered at the altitude of fragmentation. For Chelyabinsk, the peak energy deposition occurred at an altitude of roughly 27 kilometers. The total energy released was approximately 500 kilotons of TNT equivalent, making it the most powerful airburst event recorded since the development of modern instruments. Now, here is the part that changes how you should think about asteroid danger. The Chelyabinsk object was small. 20 meters across is tiny by asteroid standards. It would not even qualify as a potentially hazardous asteroid under NASA's official definition. It was well below the 140-meter threshold that Congress mandated NASA to track, and yet it released energy equivalent to a substantial nuclear weapon, injured over 1,000 people, and caused tens of millions of dollars in property damage across a major metropolitan region. If the entry angle had been steeper, if the object had been slightly larger, or if it had been made of iron instead of stone, the outcome could have been radically different. A direct vertical entry would have concentrated the energy release at lower altitude, delivering a far more intense shockwave to the surface. A denser composition would have resisted fragmentation longer, allowing the object to penetrate deeper before detonating. And a slightly larger diameter, say 50 meters instead of 20, would have produced not a 500 kiloton airburst, but something in the range of 10 to 20 megatons. That is the energy of the largest nuclear weapon the United States ever tested, detonated in the sky above a populated region. This is why size alone is a dangerously incomplete measure of asteroid risk. The destructive potential of any given impact depends on at least 6 interlocking variables, and each one can shift the outcome from a dramatic light show to a regional catastrophe. The first variable is velocity. Asteroids strike Earth at speeds ranging from roughly 11 kilometers per second, the minimum for an object falling from interplanetary space into Earth's gravity well, to over 70 kilometers per second for a long-period comet arriving from the outer solar system on a retrograde orbit. Kinetic energy scales with the square of velocity. That means doubling the speed does not double the energy, it quadruples it. An asteroid travelling at 40 kilometers per second carries 4 times the kinetic energy of an identical object moving at 20 kilometers per second. A comet fragment arriving at 70 kilometers per second carries over 40 times the energy of a slow-moving asteroid at 11. The same rock at different speeds produces wildly different consequences. A 30-meter stony asteroid arriving at 12 kilometers per second might produce a modest airburst with limited ground damage. The same 30-meter object arriving at 60 kilometers per second as part of a cometary debris stream would release energy comparable to a multi-megaton nuclear detonation. For reference, typical near-Earth asteroid encounter velocities cluster between 15 and 25 kilometers per second. These are already extraordinary speeds. 20 kilometers per second is roughly 72,000 kilometers per hour. A rifle bullet travels at about 1 kilometer per second. The asteroids we are discussing are arriving 20 to 70 times faster than a bullet. At 20 kilometers per second, a rock the size of a house crosses the entire width of Manhattan in less than a quarter of a second. There is no human reaction time at these velocities. There is no warning you could see with your eyes. The object arrives, and the physics unfolds before your nervous system finishes processing the flash of light. The second variable is composition. Not all asteroids are made of the same material, and what an asteroid is made of determines how it interacts with the atmosphere and what it does to the surface. There are 3 broad compositional categories relevant to impact physics. Stony asteroids, which include ordinary chondrites and carbonaceous chondrites, are the most common type among near-Earth objects. They are made primarily of silicate minerals, sometimes with organic compounds and water-bearing clays. Stony asteroids are relatively fragile. They tend to fragment at higher altitudes, distributing their energy across a wider area. The Chelyabinsk impactor was a stony asteroid. It broke apart high in the atmosphere and delivered its energy as a broad shockwave rather than a concentrated ground strike. This is actually the best-case scenario for an impact of that energy level. The atmosphere acted as a shield, absorbing and spreading the blow. Iron asteroids are a different beast entirely. Composed primarily of nickel-iron alloy, these objects are dense, structurally strong, and far more resistant to atmospheric fragmentation. An iron asteroid of the same diameter as the Chelyabinsk object would not have broken apart at 30 kilometers altitude. It would have punched through the atmosphere largely intact, decelerating only modestly, and struck the ground at hypersonic speed. The result would be a crater, a fireball, and a ground-coupled shockwave far more destructive than an airburst at altitude. Iron asteroids represent a relatively small fraction of the overall near-Earth population, perhaps 5 to 8%, but they are disproportionately dangerous at small sizes precisely because the atmosphere cannot stop them. The famous meteor crater in Arizona, a bowl nearly 1.2 kilometers across and 170 meters deep, stands as the most perfectly preserved impact crater on Earth's surface. It was created roughly 50,000 years ago by an iron asteroid estimated at only 30 to 50 meters in diameter. That is smaller than a typical city block, smaller than many commercial buildings. Yet it excavated 175 million metric tons of rock and released energy in the range of 10 megatons, equivalent to roughly 700 Hiroshima bombs. The blast would have obliterated everything within a radius of several kilometers and started fires across a much wider area. A stony asteroid of the same size at the same velocity would likely have detonated in the atmosphere and left no crater at all. Composition can mean the difference between a scary sky show and a permanent geological scar that remains visible from orbit 50 millennia later. The third category, rubble pile asteroids, presents yet another set of behaviours. Many asteroids are not solid rocks at all. They are loose aggregations of boulders, gravel, and dust held together by weak gravity and van der Waals forces. When these objects enter the atmosphere, they tend to break apart early and at high altitude. Their fragments spread widely, and the energy is dispersed across a large atmospheric volume. In some scenarios, rubble pile asteroids are less dangerous per unit of kinetic energy than solid objects, because they effectively self-destruct before reaching the ground. In other scenarios, the shower of fragments can blanket a wider area with smaller but still dangerous impacts. The third variable is impact angle. This is the one almost nobody outside the planetary defense community talks about, and it changes outcomes dramatically. An asteroid arriving at a steep angle, close to vertical, drives straight down through the atmosphere with minimal path length. It encounters less total air resistance and reaches the surface or low altitude with more of its original velocity intact. The energy is deposited in a compact area. The crater, if one forms, is roughly circular. The shock wave radiates outward symmetrically. An asteroid arriving at a shallow angle, like the Chelyabinsk object at 18 degrees, takes a long, slanting path through the atmosphere. It encounters far more air along its trajectory. It decelerates more. It deposits energy over a much longer ground track. The shock wave is elongated rather than circular, affecting a wider area but at lower peak intensity. Shallow angle impacts also increase the chance of a skip out, where the object grazes the upper atmosphere and either breaks apart at extreme altitude or, in rare cases, bounces back into space without depositing all of its energy. The 1908 Tunguska event in Siberia illustrates how angle and altitude of burst interact to determine ground-level consequences. On the morning of June 30th, an object estimated at 60 to 80 meters in diameter entered the atmosphere over the Podkamennaya Tunguska River in central Siberia. The region was among the most remote on Earth, a vast expanse of boreal forest with almost no permanent human settlement. The nearest witnesses were indigenous Evenki reindeer herders camped roughly 40 kilometers from ground zero. They reported being thrown from their tents by a blast of hot wind. Their reindeer stampeded. The trees around them burst into flame before the fire was extinguished by the shockwave itself. The object exploded at an altitude of roughly 5 to 10 kilometers, with an energy release estimated between 3 and 15 megatons of TNT. The most widely cited modern estimates converge around 10 to 12 megatons, roughly 700 to 800 times the energy of the Hiroshima bomb. The airburst flattened approximately 2,000 square kilometers of forest, knocking down an estimated 80 million trees in a radial pattern centered beneath the detonation point. The trees fell outward from the epicenter in a butterfly-shaped pattern consistent with a slightly angled burst, pointing toward an entry trajectory from the southeast. At ground zero, directly beneath the explosion, trees remained standing but were stripped of every branch and leaf, left as bare vertical poles, scorched and dead. The blast wave was detected by barometric stations across Europe. Seismic instruments registered the event thousands of kilometers away. The night skies over Europe and western Russia glowed for days afterward, from high-altitude dust and ice particles lofted into the mesosphere by the fireball's thermal plume. No crater was ever found. The object disintegrated entirely in the atmosphere. Every fragment was consumed by the explosion or scattered as microscopic particles across the blast zone. More than a century of scientific expeditions have recovered only trace evidence of the impactor itself. Tiny spherules of extraterrestrial material embedded in the soil and tree resin. The object simply ceased to exist as a coherent body. Its mass converted almost entirely into light, heat, and kinetic energy transferred to the atmosphere. But the energy release was sufficient to destroy an area roughly the size of a major city and its surrounding suburbs. If the Tunguska object had arrived 3 hours later, Earth's rotation would have placed St. Petersburg, then home to nearly 2 million people, directly beneath the trajectory. The consequences would have been catastrophic on a scale that no natural disaster in modern human history has approached. The fourth variable is location of impact. This is perhaps the most underappreciated factor in asteroid risk. The same asteroid releasing the same energy at the same altitude can produce consequences ranging from negligible to civilization-threatening, depending entirely on where it happens. An airburst over the open Pacific Ocean might generate moderate tsunamis that dissipate before reaching any populated coastline. The same airburst over London, Tokyo, or New York would kill millions of people instantly and trigger economic disruption on a global scale. An ocean impact from a larger object could generate tsunamis that devastate every coastal city within thousands of kilometers. A land impact in agricultural heartland could eject enough dust into the stratosphere to disrupt global food production for years. Roughly 70% of Earth's surface is ocean. This means the statistical majority of impacts hit water, not land. That sounds reassuring until you consider what an ocean impact actually does. When a large asteroid strikes the ocean at hypersonic speed, it does not simply splash. It punches through the water column, vaporizes enormous quantities of seawater, and blasts a transient cavity in the ocean floor if the water is shallow enough. The collapse of this cavity generates tsunamis that radiate outward in every direction. The wave heights depend on the energy of the impact, the depth of the water, and the distance to the nearest coastline. For a 150-meter asteroid striking the deep Atlantic, models suggest tsunami wave heights of 10 to 30 meters at continental coastlines hundreds of kilometers away. Those waves would penetrate kilometers inland in low-lying areas, potentially affecting hundreds of millions of people. Even a smaller impact in the ocean can be devastating, in ways that a land impact of the same energy might not be. A 50-meter asteroid striking deep water generates waves that propagate efficiently across vast distances. The energy spreads radially, losing intensity with distance, but the ocean acts as a transmission medium that carries destructive force far beyond the immediate impact zone. A land impact of equivalent energy would be catastrophic locally, but contained to a blast radius measured in tens of kilometers. An ocean impact of the same energy broadcasts its consequences across an entire ocean basin, putting every low-lying coastal city within thousands of kilometers at risk. In a world where roughly 40% of the human population lives within 100 kilometers of a coastline, ocean impacts represent a uniquely distributed threat that no evacuation plan could fully address. The contrast with a land impact on an uninhabited region is stark. A Tunguska-scale event over the Sahara Desert or the open steppes of Central Asia would flatten sand dunes or grassland, produce a spectacular atmospheric display, and harm essentially no one. The same event over Mumbai or Shanghai would be among the worst disasters in recorded human history. The asteroid does not care where it lands. Geography is the final roll of the dice, and it is entirely beyond human control. The fifth variable is warning time, which we introduced conceptually earlier, but in the context of impact physics, warning time determines something very specific. It determines whether authorities can evacuate, whether deflection missions can be launched, and whether the impact is a disaster we chose not to prevent or a disaster we could not prevent. A 50-meter asteroid discovered 10 years before impact can, in principle, be deflected using existing or near-term technology. The same asteroid discovered 3 weeks before impact cannot be deflected by any means currently available to humanity. There is no spacecraft on any launch pad that can reach an asteroid in 3 weeks and alter its course. There is no nuclear device that can be deployed and positioned in that time frame to disrupt the object. Even evacuation becomes functionally impossible for a major metropolitan area in 3 weeks, especially when the impact corridor might span hundreds of kilometers and the precise strike point might remain uncertain until the final hours. The warning time is the physics of human response capability, and it is every bit as deterministic as the physics of the impact itself. The sixth variable is often the least discussed but among the most consequential. Whether the impact is an airburst or a ground strike, these two modes of energy delivery produce fundamentally different damage patterns. An airburst, where the asteroid disintegrates in the atmosphere, delivers energy as a spherical shockwave expanding outward from the point of detonation. The peak overpressure at ground level depends on the burst altitude and the total energy. Higher bursts spread energy over larger areas, but at lower peak intensities. Lower bursts concentrate energy in smaller areas at higher peak intensities. There is an altitude specific to each combination of energy and target, where the ground level overpressure is maximized. Nuclear weapons strategists call this the optimal burst height, and the same physics applies to asteroid airbursts. A ground strike, where the object survives atmospheric transit and hits the surface intact, delivers energy through a completely different mechanism. The kinetic energy is converted into a combination of seismic waves, thermal radiation, ejecta, and crater formation. The ground-coupled seismic pulse can trigger earthquakes far from the impact site. The ejecta, rock and soil blasted into the atmosphere at high velocity can rain down over enormous areas, starting fires and causing secondary destruction hundreds of kilometers from ground zero. For large impacts, the ejecta can reach the stratosphere and circle the globe, blocking sunlight and causing prolonged climate effects. The interplay of these 6 variables creates a matrix of possible outcomes so complex that no single number, not diameter, not energy, not probability, can capture the full picture of what any given asteroid might do. 2 objects of identical size can produce wildly different consequences based on their speed, composition, angle of arrival, and where they happen to hit. This is why planetary defense scientists do not simply rank asteroids by diameter and call it a day. They model scenarios, they calculate impact corridors, they assess probabilities across multiple variables simultaneously, and they acknowledge, with uncomfortable honesty, that prediction is only as good as the data feeding the models. This complexity also explains why the public conversation about asteroid danger is almost always oversimplified. Media coverage tends to focus on diameter. How big is the asteroid? Is it the size of a car, a house, a football stadium? These comparisons are intuitive, but misleading. Telling someone an asteroid is the size of a football stadium says nothing about how fast it is moving, what it is made of, whether it will hit land or water, or whether it will explode in the atmosphere or reach the surface. 2 stadium-sized asteroids can differ in destructive potential by a factor of 100 depending on their other physical properties. The gap between a city-scale disaster and a civilization-ending catastrophe is not a smooth gradient. It is a series of thresholds where the physics changes qualitatively, not just quantitatively. Below roughly 25 meters, most stony asteroids break apart harmlessly in the upper atmosphere. They produce bright fireballs, sometimes meteorite falls, occasionally broken windows, but no widespread destruction. Between 25 and 50 meters, you enter the Chelyabinsk to Tunguska range, where airbursts can damage or destroy infrastructure across areas measured in hundreds to thousands of square kilometers. Between 50 and 140 meters, the consequences escalate to potential city destruction, significant tsunamis from ocean impacts, and casualties potentially measured in hundreds of thousands depending on location. Between 140 meters and 1 kilometer, you cross into regional to continental devastation. Impacts at this scale can affect global agriculture through dust injection, trigger firestorms across thousands of square kilometers, and produce tsunamis that threaten entire ocean basins. Above 1 kilometer, the consequences become global. A 1 kilometer asteroid impact releases energy equivalent to roughly 100,000 megatons of TNT, enough to inject sufficient dust and soot into the stratosphere to reduce global temperatures by several degrees for years. Crop failures, mass starvation, economic collapse, and potentially the death of billions of people become plausible outcomes. Above 10 kilometers, you reach the Chicxulub threshold, the mass extinction class, where the energy release is sufficient to fundamentally alter the global environment for decades or centuries. The good news is that larger asteroids are rarer. The population distribution follows a steep power law. For every 1 kilometer near-Earth asteroid, there are roughly 1,000 objects in the 100-meter range. For every 100-meter object, there are tens of thousands in the 10-meter range. The probability of impact scales with population, meaning smaller strikes happen more frequently and larger strikes happen more rarely. A Chelyabinsk scale event occurs roughly once every 50 to 100 years on average. A Tunguska scale event occurs roughly once every 500 to 1,000 years. A 1-kilometer impact occurs roughly once every 500,000 years. A Chicxulub-class extinction event occurs roughly once every 100 million years. These frequencies sound reassuring until you remember that they are averages over geological time. An average recurrence interval of 500 years does not mean the next event is 500 years away. It does not mean we get 499 years of safety after the last one. It means that in any given year, there is roughly a 1 in 500 chance of it happening, regardless of when the last event occurred. The asteroids do not keep a calendar. They do not space themselves politely across the centuries. The intervals are random. You could have 2 Tunguska scale events in the same decade, followed by 3,000 years of quiet. Or you could have the next one tomorrow. Probability does not guarantee spacing. This statistical reality is deeply counterintuitive for human psychology. We evolved to think in terms of patterns and cycles. Seasons repeat. Tides follow the moon. Day follows night. We instinctively expect threats to follow predictable rhythms. Asteroid impacts do not. They are governed by orbital mechanics and random chance, not by any cycle that the human brain can track or predict. The only way to manage a random threat is constant vigilance, not periodic concern. Roll that die enough times, and you will eventually hit. The question is never if. The question is always when, and whether we will see it coming with enough lead time to act. This brings us back to the central problem. The physics of asteroid danger is well understood. Scientists can model impact scenarios with extraordinary precision. They can calculate blast radii, tsunami heights, ejector distributions, and climate effects for any combination of size, speed, composition, angle, and location. The models work. The physics is not the problem. The problem is input data. Every model requires knowing what is coming, how fast, from what direction, and how soon. And for a disturbingly large fraction of the near-Earth asteroid population, we do not yet have that information. The detection gap we discussed earlier is not just a statistical inconvenience. It is a gap in the input data for every impact model ever built. Without knowing an object exists, you cannot model its threat. Without modeling its threat, you cannot assess its risk. Without assessing its risk, you cannot decide whether to deflect it, evacuate under it, or ignore it. The machinery that bridges this gap, the global network of telescopes, radars, automated monitoring systems, and international coordination frameworks that collectively form humanity's planetary defense infrastructure, is the subject of what comes next. Because understanding what an asteroid can do is only half the equation. The other half is understanding how we find them, how we calculate their odds, and what happens inside the system when an object moves from unknown to known to potential threat. That process is more sophisticated than most people imagine, more fragile than most people realize, and more consequential than anything else happening in science right now. Somewhere in the mountains of Arizona, a telescope is staring at a patch of sky that looks completely empty. The camera shutter opens. Photons that have been traveling through space for minutes, hours, sometimes days, strike a silicon sensor cooled to nearly -100 degrees Celsius. The exposure lasts 30 seconds. The shutter closes. Another exposure begins on the same patch of sky 15 minutes later. Then another, 30 minutes after that. When the sequence is complete, software compares the 3 images pixel by pixel, looking for one specific signature, a dot that moved. Stars do not move between frames on this timescale. Galaxies do not move. Cosmic rays produce random bright specks, but they appear in only one frame, never 3. The only objects that shift position consistently across 3 exposures taken over the span of an hour are things inside our solar system. things close enough and moving fast enough to produce detectable motion against the fixed background of stars. When the software identifies a moving dot that appears in all three frames, following a straight or gently curved path, it flags the detection. A human operator reviews the flag, confirms it is not an artifact or a known satellite, and submits the positional measurements to the Minor Planet Center in Cambridge, Massachusetts. The entire process from photon to report can take less than a day. This is how an asteroid is born into human awareness, not with a dramatic telescopic photograph of a tumbling rock silhouetted against the stars, not with a red alert flashing on a government screen, not with a phone call from a scientist to a president. It begins as 3 dots on a sensor, a whisper of motion in a sea of stillness. And from those 3 dots, the entire machinery of planetary defense begins to turn. The first thing that happens when positional measurements arrive at the Minor Planet Center is orbit determination. 3 observations of a moving object, each consisting of a precise sky position and a precise time, provide enough information to calculate a preliminary orbit using methods that date back to Carl Friedrich Gauss in 1801. The mathematics is well established. Given 3 points on an object's path across the sky, you can solve for the 6 orbital elements that describe its elliptical trajectory around the Sun. These elements tell you the shape of the orbit, its orientation in 3-dimensional space, and where the object was at a specific reference time. From those 6 numbers, you can project the object's position forward and backward in time indefinitely. In theory. In practice, 3 observations spanning a single night produce an orbit with enormous uncertainty. The measurements themselves carry small errors from atmospheric distortion, sensor noise, and the difficulty of pinpointing the exact center of a faint smear of light on a detector. These measurement errors propagate through the orbital calculation and inflate the uncertainty in the predicted future position of the object. After one night of observation, you might know the asteroid's orbit well enough to predict where it will be next week to within a few thousand kilometers. But predicting where it will be in 10 years could carry an uncertainty of millions of kilometers, and predicting where it will be in 50 years might be functionally meaningless. This is why follow-up observations are critical. Every additional night of tracking data tightens the orbital solution. The uncertainty region, the volume of space where the asteroid could plausibly be at a future date, shrinks with each new measurement. After a week of observations, the orbit improves dramatically. After a month, it improves further. After multiple observing windows spanning years, as the asteroid appears, disappears behind the Sun, and reappears on the other side, the orbit can become precise enough to predict positions decades into the future, with confidence measured in hundreds of kilometers rather than millions. This process explains a pattern that confuses and frightens the public every time. It plays out. When a new asteroid is first discovered, its impact probability often increases before it decreases. This seems counterintuitive. You discover an asteroid, and the chance it hits Earth goes up? That makes no sense to a normal person reading a headline. Except it does happen, consistently, and it is a perfectly normal consequence of how orbital uncertainty works. Understanding this pattern is essential to understanding why asteroid news so often triggers unnecessary panic. When an asteroid is first detected, the uncertainty region is large. Imagine a 3-dimensional cloud stretching millions of kilometers along the asteroid's projected future path. Every point within that cloud represents a possible position the asteroid could occupy at a given future date. The cloud is not uniformly dense. Some positions are more probable than others based on the observed trajectory. Within that vast cloud of possible trajectories, the fraction that happen to intersect Earth is typically tiny. The initial impact probability might be 1 in 10 million. A sliver of the cloud overlaps with Earth's position. The rest does not. As new observations come in during the first few days, the uncertainty region shrinks. The cloud compresses. Impossible trajectories are eliminated. But the cloud does not shrink uniformly in every direction. Sometimes the early observations eliminate trajectories that would have missed Earth by wide margins, while leaving the portion of the cloud near Earth's position relatively intact. When you eliminate harmless trajectories faster than dangerous ones, the fraction of remaining possibilities that are dangerous increases. The probability goes up because the remaining possibilities are more concentrated near the dangerous zone. This can continue for days or even weeks, producing headlines about rising impact odds that terrify the public and fuel conspiracy theories about government cover-ups. Then, almost always, the critical observations arrive. A few more nights of data eliminate the dangerous trajectories as well. The probability plummets, often to zero. The asteroid is removed from the risk table. The scare was never real. The system was simply doing its job, narrowing down uncertainty from the outside in, and the dangerous region happened to be the last part eliminated rather than the first. Scientists understand this pattern intimately and expect it every time a new object appears on the risk table. The public does not, and has no reason to. The mathematics of Bayesian orbit refinement is not something anyone should need to understand to read the morning news. But the communication gap is real, and every time the pattern plays out in public view, it erodes trust in the very institutions doing the work of keeping us safe. The tools that communicate risk to the public and to decision makers are the Torino scale and the Palermo scale. They serve very different purposes and are designed for very different audiences. The Torino scale was created specifically for public communication. It ranges from 0 to 10 and combines two factors: the probability of impact and the energy of the potential collision. A rating of 0 means the object poses no unusual level of danger. The likelihood of collision is essentially 0, or the object is so small that it would disintegrate harmlessly in the atmosphere even if it did hit. A rating of 1 means the object merits careful monitoring but poses no cause for public concern. Ratings of 2 through 4 indicate objects that merit concern and close attention from astronomers, with increasing levels of probability or consequence. 5 through 7 describe objects where the probability of a large regional to global impact is disturbingly credible. 8 through 10 describe certain or near certain collisions, escalating from regional destruction at 8 to global catastrophe at 9 and 10. In the entire history of the Torino scale, no object has ever been rated above 4. Apophis briefly reached 4 in 2004, when early calculations suggested a 2.7% chance of impact in 2029. Asteroid 2024 YR4 reached 3 in early 2025. Both were subsequently downgraded to 0 as additional observations refined their orbits. Only one other object has ever exceeded a rating of 1, Asteroid 2004 VD17, which briefly reached 2 in 2006 before also being downgraded. This is not because dangerous asteroids do not exist. It is because the objects large enough to rate highly are also the ones most likely to have been discovered long ago, when their orbits were still far from any close approach. The truly dangerous unknowns, by definition, have not yet been rated at all. The Palermo scale serves a different function. It is a logarithmic technical scale designed for scientists rather than the public. It compares the probability of a specific impact event to the background probability of an impact of equivalent or greater energy occurring randomly during the same time interval. A Palermo rating of 0 means the specific threat is exactly equal to the background risk. A rating of -2 means the specific threat is 100 times less likely than the background risk over the same period. A rating of +2 means the specific threat is 100 times more likely than background. No object currently on any risk table has a positive Palermo rating. The highest rated objects sit around -1 to -2, meaning they represent threats that are still well below the baseline random risk of an equivalent impact occurring from an unknown source. This distinction matters enormously for understanding what the risk tables actually tell us. The Planetary and ESA risk tables are not lists of asteroids that are going to hit Earth. They are lists of asteroids whose orbital uncertainty has not yet been reduced enough to completely rule out an impact. The vast majority will be removed as observations continue. The few that linger do so because they are small, faint, and difficult to track. making follow-up observations challenging. One of the most important concepts in impact risk assessment is the gravitational keyhole. A keyhole is a small, precisely defined region of space near Earth through which an asteroid must pass during a close approach in order to be placed onto a trajectory that leads to an impact on a subsequent orbit years or decades later. The keyhole is not a physical object. It is a mathematical construct, a window in the asteroid's uncertainty region that corresponds to a very specific set of gravitational perturbations from Earth. Think of it this way. When an asteroid passes close to Earth, our planet's gravity bends its trajectory. The exact amount of bending depends on the precise distance and geometry of the flyby. Most flyby trajectories send the asteroid onward into harmless orbits that never return to our vicinity. But a tiny subset of trajectories, corresponding to passage through the keyhole, redirect the asteroid onto a resonant path that brings it back to Earth's exact location at a specific future date, years or decades later. Keyholes are typically measured in hundreds of meters to a few kilometers across, astonishingly small windows in the fabric of orbital mechanics. They are unimaginably small compared to the uncertainty regions of newly discovered asteroids, which can span millions of kilometers. This is why keyhole-related impact probabilities start astronomically low and only become concerning if the asteroid's orbit is refined to the point where the uncertainty region shrinks to a size comparable to the keyhole itself. The difficulty of predicting whether an asteroid will thread a keyhole is compounded by the Yarkovsky effect. This phenomenon deserves a closer look because it is one of the most counterintuitive forces in orbital mechanics and one of the most important for long-term impact prediction. As an asteroid rotates, the side facing the Sun absorbs solar radiation and heats up, but that heated surface does not re-radiate the thermal energy instantaneously. There is a delay, a thermal lag, just as a sunlit sidewalk remains warm after sunset. By the time the heated surface radiates its peak thermal energy, the asteroid has rotated, and that surface now faces a different direction. The emitted thermal photons carry momentum, and by Newton's third law, the asteroid receives a tiny push in the opposite direction. The net effect is a continuous, gentle thrust that acts along or against the asteroid's orbital motion depending on the direction of spin. For a prograde rotator, one spinning in the same direction as its orbit, the Yarkovsky effect pushes the asteroid slightly outward, gradually increasing its orbital period. For a retrograde rotator, spinning opposite to its orbital direction, the effect pushes inward, shrinking the orbit. The force is absurdly small. For a 100-meter asteroid, it might amount to a fraction of a Newton, less than the weight of a single apple on Earth. But it acts continuously, day after day, year after year, decade after decade. Over a century, it can shift an asteroid's position along its orbit by tens or hundreds of kilometers. That displacement is small compared to the orbit itself, but enormous compared to the size of a gravitational keyhole. Whether an asteroid threads a keyhole or misses it by a comfortable margin can depend entirely on whether you correctly account for the Yarkovsky effect in your orbital model. Apophis and gravitational keyholes are inextricably linked in the history of planetary defense. When Apophis was discovered in June 2004 at the Kitt Peak National Observatory in Arizona, initial orbital calculations quickly revealed it was on a trajectory that would bring it extraordinarily close to Earth in 2029. Within months, the impact probability for that encounter rose to 2.7%, the highest ever recorded for any known asteroid. Apophis was assigned a Torino scale rating of 4, a level described as meriting concern by the public and close attention by astronomers. The asteroid was named after the Egyptian deity of chaos and destruction. The name was earned. Over the following years, continued observations steadily refined the orbit and reduced the impact probability for 2029 to 0. Earth was safe from a direct hit during that flyby. But a new concern emerged. During the 2029 close approach, Apophis will pass approximately 32,000 kilometers from Earth's surface, closer than the geostationary satellites that relay our television signals and internet data. At that distance, Earth's gravity will significantly alter the asteroid's orbit, widening it and shifting Apophis from the Aten orbital group to the Apollo group. The question became whether Apophis might thread a gravitational keyhole during the 2029 flyby that would place it on a collision course for a later return, potentially in 2036 or 2068. This question haunted planetary defense scientists for nearly 2 decades. Resolving it required extraordinary observational precision. Radar observations from NASA's Goldstone Deep Space Communications Complex and the Green Bank Observatory in March 2021 provided measurements accurate enough to determine the Yarkovsky effect on Apophyses' orbit with the highest precision ever achieved for any asteroid. The Yarkovsky effect, that subtle thermal thrust caused by an asteroid absorbing sunlight and re-radiating heat as it rotates, shifts Apophis' orbital position by approximately 170 meters per year. Over decades, this accumulates into kilometers of displacement, enough to determine whether the asteroid passes through a keyhole or misses it. The 2021 radar campaign delivered the definitive answer. Apophis will not pass through any gravitational keyhole during the 2029 flyby. There is no impact risk from Apophis for at least the next 100 years. The asteroid was formally removed from both NASA's and ESA's risk lists in March 2021. The crisis that began in 2004 was over, but Apophis is far from finished as a subject of scientific interest. Its 2029 flyby will be the closest approach of an asteroid this large that scientists have ever predicted in advance. Apophis is approximately 340 meters in diameter, roughly the height of the Eiffel Tower. On April 13th, 2029, a Friday, it will be visible to the naked eye from parts of Europe, Africa, and Western Asia, appearing as a moderately bright point of light moving rapidly across the sky. An estimated 2 billion people will be able to witness the event without any optical aid. A close approach of this magnitude for an object of this size occurs on average once every 7,500 years. 3 spacecraft are being prepared to study Apophis during the flyby. NASA's OSIRIS-APEX, the repurposed OSIRIS-REx probe that successfully returned samples from asteroid Bennu in September 2023, will rendezvous with Apophis shortly after the close approach and study it for 18 months. ESA's Ramses mission, based on the Hera spacecraft design, aims to reach Apophis before the flyby and accompany it through the encounter, capturing before and after observations of how Earth's gravity physically alters the asteroid's shape, spin rate, and surface. Japan's Destiny Plus mission is also planning observations. Together, these missions will provide the most detailed study of a potentially hazardous asteroid ever conducted, generating data that will directly inform how humanity would respond to a future asteroid that is not going to miss. The technology for that response is no longer theoretical. In September 2022, NASA's DART spacecraft deliberately crashed into the asteroid moonlet, Dimorphos, at a speed of roughly 6.1 kilometers per second. Dimorphos, approximately 151 meters across, orbits a larger asteroid called Didymos. The impact shortened Dimorphos's orbital period around Didymos by approximately 33 minutes, far exceeding the minimum benchmark of 73 seconds that mission planners had set for success. The collision ejected thousands of tons of rocky debris from Dimorphos's surface, creating a tail of material visible from ground-based telescopes for weeks. The momentum from this ejected debris roughly doubled the effectiveness of the kinetic impact, meaning the asteroid received nearly twice the push from the debris cloud as it did from the spacecraft impact itself. But the most significant result came later. In March 2026, a study published in the journal Science Advances confirmed that the DART impact did not merely alter Dimorphos's orbit around Didymos. It measurably changed the orbit of the entire binary asteroid system around the Sun. This is the first time in human history that a human-made object has demonstrably altered the heliocentric trajectory of a celestial body. The deflection was tiny in absolute terms, measured through extraordinarily precise techniques including stellar occultations where the asteroid briefly blocks the light of a background star. But the principle is proven. Kinetic impact works. Humanity can push an asteroid off course. ESA's Hera spacecraft, launched in October 2024, is expected to arrive at the Didymos system in late 2026. Hera will conduct a detailed post-impact survey, measuring Dimorphos's mass, internal structure, crater shape, and the precise orbital changes resulting from the DART impact. This data is essential for scaling up the kinetic impactor technique. DART demonstrated the principle. Hera will provide the engineering parameters needed to apply it to a real threat. The Vera-C. Rubin Observatory in Chile represents the next major leap in ground-based detection capability. Currently in its commissioning phase, Rubin will conduct the Legacy Survey of Space and Time, a 10-year survey that will image the entire visible southern sky every few nights, using an 8.4-meter primary mirror and the largest digital camera ever built for astronomy. The survey is expected to dramatically increase the rate of near-Earth object discovery, potentially finding more new objects in its first year of operation than all previous surveys combined over the past 2 decades. Rubin's wide field of view and deep sensitivity will be particularly effective at detecting smaller asteroids in the 50 to 100 meter range that current surveys struggle to find. Together, these capabilities represent a planetary defense infrastructure that would have been unimaginable a generation ago. Automated survey telescopes scan the sky every clear night. The Minor Planet Center coordinates global observations in near real time. Sentry 2 evaluates impact risks automatically for every known near-Earth object. The International Asteroid Warning Network connects observatories worldwide into a coordinated response framework. The Space Mission Planning Advisory Group, chaired by ESA, serves as the international forum for coordinating spacecraft-based responses to potential threats. DART has proven that deflection works. Hera is refining the engineering. OSIRIS Apex and Ramses will study the most scientifically valuable close approach in modern history. NEO Surveyor will open the sunward blind spot. Vera Rubin will flood the catalogues with new discoveries. And yet, the system has limits that no amount of engineering can fully erase. Ground-based telescopes remain blind in the solar direction and during cloudy weather. A significant fraction of potentially hazardous asteroids spend much of their orbits in the sunward blind spot, invisible to every survey telescope on Earth's surface. Space-based assets are expensive, few in number, and take years to build and launch. Until NEO Surveyor reaches its operational station, that blind spot remains open, a gap in our perimeter that any asteroid can pass through undetected. The Vera Rubin Observatory will find enormous numbers of new asteroids, but each discovery creates a downstream demand for follow-up observations. An asteroid discovered by Rubin must be tracked by other telescopes over subsequent nights and weeks to refine its orbit sufficiently for meaningful risk assessment. The follow-up telescope time is a bottleneck that cannot be expanded overnight. Observatories that currently provide follow-up tracking are already stretched thin. When Rubin begins flooding the Minor Planet Center with thousands of new detections per month, the rate-limiting step in the pipeline will shift from discovery to characterization. Finding the asteroids is only the beginning. Understanding their orbits well enough to determine whether they are dangerous takes sustained effort from a network that is, in many cases, operating on academic budgets and volunteer labor. Small asteroids below 25 meters remain essentially untrackable with current technology. They are too faint, too numerous, and too fast-moving to catalog systematically. Most will never be detected until they are already inside Earth's atmosphere. The Chelyabinsk impactor at 18 meters was not an unusual failure of the system. It was a normal outcome for an object of that size. Current surveys are simply not designed to find objects that small. They can detect them occasionally if the geometry is favorable, but systematic coverage of the sub-25-meter population is beyond anything currently planned or funded. Long-period comets arriving from the Oort cloud on near-parabolic orbits present a qualitatively different kind of threat. Unlike near-Earth asteroids, which orbit the Sun on predictable paths and can be tracked over multiple apparitions spanning years, long-period comets may never have visited the inner solar system before. They appear without precedent, entering the detection zone for the first time only months before a potential close approach. A large long-period comet on a collision course with Earth might be discovered with as little as 6 to 12 months of warning, possibly less. That is not enough time to design, build, and launch a deflection mission. It might barely be enough time for a nuclear standoff detonation, the most energetic deflection option available, assuming one could be assembled and launched on an emergency timeline. For a large comet nucleus, even nuclear deflection might prove insufficient without years of lead time, and any deflection technique, whether kinetic impact, gravity tractor, ion beam deflection, or nuclear standoff detonation, requires years of lead time to design, build, launch, travel to the target, and execute with confidence. DART travelled for 10 months to reach Dimorphos. A mission to deflect a threatening asteroid discovered 5 years before impact would need to launch within the first 2 years to allow sufficient travel time, rendezvous, and margin for the deflection to accumulate. That leaves only 2 years for mission design, spacecraft construction, testing, and launch preparations, a timeline that would strain even the most capable space agencies on Earth. A threatening asteroid discovered 2 years before impact is, in all practical terms, undeflectable with current technology. Evacuation becomes the only option, and evacuating tens of millions of people from an impact corridor that might not be precisely known until the final days is a logistical challenge that no government on Earth has ever rehearsed at scale. The detection machine is real. It works. It is improving every year. But it is a machine built by a species that has been seriously looking for near-Earth asteroids for only about 3 decades, that has successfully deflected exactly 1 asteroid in its entire history, and that still has not catalogued more than half of the objects large enough to threaten a city. The machine is running. The question that defines our era of planetary defense is whether it will be fast enough, whether the next object that matters will be found with decades of lead time, giving us every option, or whether it will be found with weeks of lead time, giving us none. What comes next confronts that question directly, because the final stretch of this story is not about the asteroids themselves. It is about the permanent reality of living on a planet embedded in a field of debris, and what that reality demands of a civilization capable of seeing the danger, but still learning how to respond to it. Here is the single most important sentence in this entire story. There is currently no known significant asteroid impact threat to Earth for the next 100 years or more. That is the official assessment of NASA's Planetary Defense Coordination Office, ESA's Near-Earth Object Coordination Center, and every credible scientific institution on the planet that monitors this problem. It is not a guess. It is not an approximation. It is the output of automated systems that continuously evaluate the orbits of every known near-Earth object, projecting their trajectories a century into the future and checking for any intersection with our planet. The systems have been running for over 2 decades. They have been refined, upgraded, and cross-checked by independent teams on different continents using different software and different observational data. The answer is consistent. No known object currently poses a significant collision threat on any timescale relevant to your life, your children's lives, or your grandchildren's lives. That sentence should reassure you. It is designed to, and it is honest, but it is not the end of the story. It is not even the most important part of the story, because the word that carries all the weight in that sentence is not threat or significant or 100 years. The word that matters is known. We have spent this entire journey so far building the architecture of understanding you need to grasp what that qualifier truly means. You now understand that the near-Earth asteroid population is estimated at roughly 25,000 objects above 140 meters, and that we have catalogued fewer than half. You understand that millions of smaller objects in the 20 to 100 meter range orbit near Earth essentially uncounted. You understand that asteroids approaching from the sunward direction are invisible to ground-based telescopes and will remain so until dedicated space-based infrared observatories become operational. You understand that long-period comets can arrive from the outer solar system with months of warning rather than decades. You understand that even a modest object of 50 meters can produce destruction equivalent to the largest nuclear weapons ever tested if the entry geometry and impact location align unfavorably. You also understand that the detection and deflection infrastructure humanity has built is genuinely impressive and improving rapidly. Survey telescopes scan the sky every clear night. Automated systems evaluate risk in real time. We have successfully deflected an asteroid for the first time in history. Spacecraft are en route to study the aftermath. New observatories and dedicated space telescopes are under construction. The planetary defense community is real, professional, funded, and effective within the scope of what it has been given to work with. The tension between those two realities is the actual story of asteroid danger. Not a single terrifying rock with a name and a countdown. Not a secret that governments are hiding. The story is the gap between what we have accomplished and what the problem requires. The story is that we are building the walls of a fortress while living inside an active shooting range, and the construction is not yet finished. Let us be precise about what the residual risk actually looks like, because precision is the antidote to both complacency and panic. The first category of residual risk is undiscovered large objects. For every asteroid above the 140-meter threshold that we have found and cleared, there is roughly one more that we have not found at all. The remaining objects are not hypothetical. They are real rocks on real orbits, carrying real kinetic energy, occupying real positions in space that no instrument has yet recorded. They exist right now, today, some of them possibly on trajectories that will bring them close to Earth within years or decades. We simply do not know. And that ignorance is not a gap in knowledge that can be dismissed with a shrug. When you multiply the vanishingly small probability that any single undiscovered object is on a collision course by the thousands of objects that remain uncatalogued, the aggregate risk is not negligible. It is, in fact, the dominant source of impact risk facing our planet. The known objects have been evaluated and cleared. The danger overwhelmingly resides in the unknown. The second category is the sub-140-meter population. These objects are too small to trigger the kind of global catastrophe that extinction-class impacts produce, but they are large enough to destroy cities, devastate regions, and kill millions if the geography of impact cooperates. A 70-meter iron asteroid striking the eastern seaboard of the United States would release energy in the tens of megatons range and could produce a blast zone encompassing an area larger than any single metropolitan region. The same object striking the remote interior of Antarctica would be a footnote in a scientific journal. The difference is geography, not physics, and geography is random. We do not get to choose where the next impact occurs. We only get to choose whether we see it coming. The third category is the long-period comet threat, the one we explored earlier as a fundamental limitation of the detection system. Unlike asteroids, which return on predictable schedules and can eventually all be catalogued, a long-period comet may give us only months between first sighting and closest approach. That window is too short for deflection and possibly too short for meaningful evacuation. What makes this category uniquely disturbing is not its probability, which is very low in any given century, but its unmitigability. It is the one class of impact threat against which no current technology offers a reliable defense regardless of how much warning time we have. It is the residual risk that remains even after every asteroid in the catalogue has been found, tracked, and cleared. The only response available is continued monitoring and the hope that future detection capabilities will push the warning window far enough forward to make action possible. These three categories of risk interact to create a landscape that is fundamentally different from how the public imagines asteroid danger. Most people, if they think about it at all, picture a binary scenario. Either a specific asteroid is coming and we are doomed, or no asteroid is coming and we are fine. The actual situation is probabilistic, continuous, and permanent. There is no moment when the threat is resolved. There is no day when the last dangerous asteroid is found, and we can declare victory. The solar system will continue producing new near-Earth objects through gravitational perturbations of main belt asteroids for billions of years. Collisions within the asteroid belt fragment larger bodies into smaller ones. Jupiter's gravity nudges fragments onto eccentric orbits that cross the inner solar system. New objects will continuously enter near-Earth space, as old ones are ejected by planetary encounters or destroyed by solar heating and tidal forces. The population is not static. It is a conveyor belt fed by the gravitational machinery of an entire solar system, and we are standing at the delivery end, counting packages as they arrive. This permanence is one of the hardest aspects of asteroid risk for the public, and for policymakers to internalize. Human institutions are designed around problems that have solutions. You build a dam to stop a flood. You develop a vaccine to end a pandemic. You sign a treaty to end a war. Asteroid defense does not work this way. It is not a problem to be solved. It is a condition to be managed. The threat does not end when we find all the big asteroids currently in near-Earth orbits, because new ones will arrive. The threat does not end when we develop reliable deflection technology, because some objects will be found too late to deflect. The threat does not end when we build better telescopes, because some objects are intrinsically difficult to detect, regardless of how capable our instruments become. This is why the comparison to other existential risks is instructive but ultimately misleading. Climate change, nuclear war, pandemic disease, these are threats generated by human activity or biological processes on Earth. They can, in principle, be eliminated or controlled through human choices. Asteroid impacts cannot. They are imposed by the physics of our solar system. They are a feature of the environment we inhabit, not a consequence of our behavior. No amount of policy, diplomacy, or social change can alter the orbit of a 60-meter stony asteroid. Only physics can do that, applied through engineering, funded by institutions, and guided by data gathered through sustained observation. The history of Apophis demonstrates both the power and the fragility of this enterprise. An object was discovered. It was assessed as dangerous. Observations over 20 years refined the risk from genuinely alarming to definitively zero. The system worked exactly as designed, producing a happy ending through the sustained application of scientific observation, mathematical analysis, and international cooperation. But that success required 2 decades of continuous effort. It required radar facilities, optical telescopes, space-based instruments, and hundreds of scientists contributing observations across multiple countries. It required funding that was never guaranteed, and institutional support that could have been withdrawn at any point by a government that decided asteroid defense was no longer a priority. What happens when the next Apophis is discovered and the system is not funded? What happens when the follow-up telescopes are decommissioned because their grants expired? What happens when the radar facilities at Goldstone are shut down for budget reasons, and the next object that needs a precision orbit determination has no instrument capable of providing one? These are not hypothetical concerns. They are active policy debates happening right now. NASA's fiscal year 2026 budget request proposed terminating the OSIRIS-APEX mission to Apophis. The NEO-Surveyor mission, after 2 decades of delays caused by repeated failures to secure funding, is finally on track for launch. But its budget has grown from an initial estimate of $500 million to roughly $1.6 billion, creating ongoing political vulnerability. The planetary defense community operates in a state of permanent precarity, dependent on the continued willingness of governments to fund a problem that has not produced a headline-generating disaster in living memory. This is the paradox at the heart of planetary defense. Success is invisible. When the system works perfectly, nothing happens. No asteroid hits, no city is destroyed, no lives are lost. The public sees no evidence that the investment was justified. The telescopes scan empty sky. The risk tables show zeros. Politicians who fund the program get no dramatic crisis to point to during re-election campaigns. The entire enterprise succeeds by producing non-events, and non-events are the hardest thing in the world to fund. Compare this to disaster response. When a hurricane strikes, the images are immediate, visceral, and politically potent. Funding flows, agencies mobilize, the public demands action, politicians compete to appear responsive. Rebuild budgets pass through legislatures in days. Asteroid defense generates no equivalent urgency because it works by preventing the disaster before it occurs. If it ever fails, the images will be orders of magnitude worse than any hurricane. But until it fails, the images do not exist. There are no photographs of a city that was not destroyed. There are no interviews with survivors who were not killed. There is no wreckage to film, no rubble to stand in front of, no moment of national solidarity in the face of shared tragedy. There is only the quiet hum of a telescope tracking a faint dot across the sky and a line in a spreadsheet that says this object will not hit Earth. That is what success looks like in planetary defense, and it is, by any measure, the least compelling footage imaginable for a 24-hour news cycle. This asymmetry between the invisibility of success and the catastrophic visibility of failure creates a structural vulnerability in the funding and political support for planetary defense. The programs survive because a relatively small number of scientists, policymakers, and advocates have been relentlessly effective at explaining the risk and securing resources year after year, administration after administration, budget cycle after budget cycle. But the margin is thin. A single administration that decides to defund asteroid surveys could set the effort back by a decade. A single budget cycle that eliminates follow-up telescope time could leave thousands of newly discovered objects with orbits too poorly known to assess for risk. The system is robust against asteroids. It is fragile against politics. And politics, unlike asteroids, changes direction unpredictably and without the courtesy of an orbital calculation. The public misunderstanding of asteroid risk makes this political fragility worse. Media coverage of asteroid close approaches almost always defaults to one of two narratives. Either the asteroid is going to hit us and we are all going to die, or the asteroid is going to miss and there is nothing to worry about. Neither narrative is accurate, neither serves the public interest. The first generates panic and erodes trust when the asteroid inevitably turns out not to be a threat. The second generates complacency and undermines the case for continued investment in detection and deflection capabilities. The accurate narrative is harder to tell because it lacks dramatic resolution. It has no villain, no countdown, no explosion, no hero saving the world in the final act. The accurate narrative is that we live in a solar system containing millions of objects capable of harming us, that we are cataloguing them as fast as our resources allow, that no known object currently threatens us, that many objects remain unknown, that our detection capabilities are improving but not yet complete, and that the entire enterprise depends on sustained funding and institutional commitment that is never guaranteed. That narrative does not fit a headline. It does not generate clicks. It does not satisfy the human craving for certainty, for a definitive answer to the simple question of whether we are safe. We are not safe. We are safer than we were 30 years ago, dramatically safer than we were a century ago, and incomparably safer than the dinosaurs were 66 million years ago. But safe is a word that implies the absence of risk, and risk is a permanent feature of our cosmic address. What we have built is not safety, it is vigilance. And vigilance, unlike safety, requires continuous effort. The case of 2024. YR4 illustrated this with uncomfortable clarity. When that 50-meter asteroid briefly rated a 3 on the Torino scale, the global response demonstrated both the strengths and the weaknesses of the current system. Astronomers coordinated observations across continents within days. The International Asteroid Warning Network activated its protocols. NASA deployed the James Webb Space Telescope, the most powerful observatory in human history, to track a tiny rock at the edge of detectability. The threat was resolved through extraordinary scientific effort, applied with speed and precision that would have been impossible even a decade earlier. But the public response was chaos. Social media flooded with misinformation. Conspiracy theories proliferated. Credible information from official sources was drowned out by sensational speculation. People who had never heard of the Torino scale or the Century system were suddenly making life decisions based on third-hand information, filtered through algorithms optimized for engagement rather than accuracy. The scientific system performed superbly. The information ecosystem failed catastrophically. And in a real emergency, where evacuation decisions depend on public trust in official communications, that failure could cost lives. The lesson is not that the public is foolish. The lesson is that the communication infrastructure for planetary defense is as underdeveloped as the detection infrastructure was 30 years ago. We have invested billions in telescopes and spacecraft. We have invested almost nothing in the public's ability to understand what those instruments tell us. The next time a genuinely threatening object appears on the risk tables, the scientific community will know exactly what to do. The question is whether the public, the media, and the policymakers will know what to do with the information they receive. This brings us to the final, most uncomfortable truth in the entire story of asteroid danger. The terrifying reality is not that a specific known asteroid is secretly guaranteed to hit Earth. Every credible source confirms that no such object exists in the current catalogue. The terrifying reality is that Earth orbits the Sun inside a field of debris that has been active for 4.5 billion years and will remain active for billions more. That debris field contains objects of every size, from dust grains to mountains. The small ones strike constantly, burning up as shooting stars in the upper atmosphere, a beautiful reminder of the violence that surrounds us. The medium ones strike occasionally, producing events like Chelyabinsk and Tunguska that would be catastrophic if they occurred over populated areas. The large ones strike rarely, on timescales measured in hundreds of thousands or millions of years, but when they do, they reshape the biological trajectory of the entire planet. The dinosaurs had no telescope. They had no space agency. They had no mathematical framework for calculating orbital trajectories. They had no ability to detect, track, or deflect the object that ended their reign. They lived on this same planet, under this same sky, surrounded by this same debris field, for over 160 million years. And then, on one ordinary day in the late Cretaceous, a rock arrived that they never saw coming, and 160 million years of evolutionary success ended in a geological instant. We are not the dinosaurs. We have tools they did not. We have knowledge they could not. We have built, in the span of a single human generation, a detection and deflection capability that transforms our relationship with this ancient threat from one of blind vulnerability to one of informed vigilance. That transformation is real and it matters, but the transformation is not complete. The walls are going up, but they are not finished. The catalogue is growing, but it is not done. The deflection technology is proven, but it has been tested exactly once. The international coordination frameworks exist, but they have never been stress tested by a confirmed incoming object. The funding is present, but it is not permanent. Every element of our planetary defense infrastructure is a work in progress, and progress requires resources, attention, and the political will to invest in a problem that punishes complacency with extinction-level consequences, but rewards vigilance with nothing more dramatic than another quiet year. The universe does not owe us another quiet year. It does not owe us warning. It does not owe us time. Every year that passes without a significant impact is not evidence that the threat is receding. It is evidence that the odds have not yet caught up with us. The next significant near-Earth asteroid impact will occur. The only variables are when, where, how large, and whether we see it coming. 3 of those 4 variables are beyond our control. The 4th, whether we see it coming, is the one variable we can influence. It is the one that justifies every telescope, every survey, Every radar observation, every spacecraft mission, every line of code in every automated monitoring system, and every dollar spent on the quiet, unglamorous, invisible work of watching the sky. Earth is 4.5 billion years old. It has been struck by asteroids continuously throughout its entire existence. The early solar system was far more violent than the present one, with impact rates hundreds of times higher during the late heavy bombardment roughly 4 billion years ago. But even the relatively calm epoch we inhabit now, this long geological afternoon of steady orbits and stable planetary spacing, is punctuated by impacts at every scale. The craters are everywhere. On the Moon, which preserves its scars because it has no atmosphere, no water, and no tectonic activity to erase them, the surface is saturated with impact basins from rim to rim. Every patch of lunar surface tells the same story. This neighborhood gets hit. Earth has endured the same bombardment on the same timescale. Our atmosphere, our oceans, our wind, our rain, and our geology have simply erased most of the evidence through erosion, plate tectonics, and the relentless recycling of the planetary surface. But the evidence that remains is unambiguous. The Chicxulub crater beneath the Yucatan, 180 kilometers across, 66 million years old. The Vredefort structure in South Africa, the largest confirmed impact crater on Earth at roughly 300 kilometers across, formed 2 billion years ago by an object estimated at 10 to 15 kilometers in diameter. The Sudbury Basin in Canada, 1.8 billion years old, created by an impactor roughly 10 to 15 kilometers wide, whose collision reshaped the geology of an entire region and deposited mineral-rich ores that are still mined today. The Chesapeake Bay impact structure, 35 million years old, buried beneath the sediments of the Atlantic coastal plain, discovered only in the early 1990s because no one had thought to look for a crater beneath the seabed of a modern estuary. These are not relics of a bygone era. They are entries in a ledger that is still being written. The ink is still wet on the most recent pages. Chelyabinsk was the latest entry, written in 2013. The next entry is already in motion somewhere in the solar system, on an orbit that will one day intersect ours. The next entry will be added. The only question is what it will say. A small airburst over an unpopulated region, noted by scientists and forgotten by the public within a week. A Chelyabinsk-scale event over a major city, killing thousands and forcing the world to confront a threat it had been content to ignore. A Tunguska-scale event over an ocean, generating tsunamis that test the emergency response capabilities of a dozen nations simultaneously. Or something larger, something rarer, something that arrives with too little warning and too much energy for any human response to matter. We cannot choose which entry comes next. We can only choose how prepared we are when it arrives, and preparation in this context means exactly what it has always meant in the story of human survival. It means watching. It means learning. It means building the tools that extend our vision beyond what our eyes alone can see. It means sustaining the institutions that turn observation into understanding and understanding into action. It means accepting that some dangers cannot be eliminated, only managed, and that management requires permanent commitment rather than periodic attention. The sky is not falling, but the sky is not empty either. Somewhere out there, right now, an asteroid is orbiting the Sun on a path that will one day bring it close to Earth. Maybe it has already been found, catalogued, and cleared. Maybe it is sitting in a database, its orbit refined to the point where scientists can say with confidence that it will pass harmlessly by. Or maybe it has never been seen. Maybe it is dark, small, moving fast, approaching from the sunward side where no telescope can reach. Maybe it will be found tomorrow by a survey telescope in Chile or Hawaii. Maybe it will be found next year by NEO surveyor from its station at the Lone Point. Or maybe it will not be found at all until it enters the atmosphere and the sky lights up. The work of planetary defense is the work of closing that gap between maybe and certainty. It is slow work. It is expensive work. It is work that produces no visible product except the continued absence of catastrophe. But it is the most important work a technological civilization can do, because it is the work that determines whether that civilization survives contact with its own cosmic environment. The dinosaurs remind us what happens when no one is watching. We are watching now. The question that will define the next century of human history is whether we keep watching, whether we invest enough, build enough, discover enough, and prepare enough to earn the safety that the universe does not give freely. The terrifying truth about the most dangerous asteroids in our solar system is not that one of them is coming to kill us. It is that the danger is permanent, the detection is incomplete, the preparation is unfinished, and the only thing standing between our civilization and the fate of the dinosaurs is a thin, underfunded, extraordinary network of telescopes, scientists, and spacecraft that most people have never heard of. That network is working right now. Tonight. While you sleep, the telescopes are open. The software is running, the sky is being watched. Whether it will be enough depends on what we choose to build next.